So we've got f with components y, negative x squared, and z squared. C is the curve of intersection of the planes x plus z equals 1 and the cylinder x squared plus y squared equals 1. And we want to evaluate the flux integral around that C. So I guess one question is, what would that look like? I'll draw a picture if you promise not to laugh at it. So if you draw, let's see, I don't know which one's easier to draw first. Probably the cylinder. I'm going to draw it without coordinates. So that's a regular tin can shaped cylinder. What's the generating curve? The unit circle in the xy plane, if you put it in the xy plane, right? So I'll just draw a rudimentary picture here. And then, yeah, the plane is going to cut it, isn't it? And so if you think about it, I'm going to draw just a quick picture of this coordinatized separately, just to make sure you guys, and this is good review for the final as well. We did all kinds of these kinds of problems in chapter 12, I think. And 15, it came up again. So x, y, and z, and then just use x-intercepts to graph the generating curve for x plus z equals 1, right? So what are both of those intercepts? So x equals 1 and z equals 1 if we just graph the non-zero part. Technically, intercepts are points, but at this level, I don't care if you call them numbers. You guys know. You guys know better, right? So in other words, what's really the x-intercept? It's not 1. What is it? It's 1, 0, 0. But you guys know that. Okay. And then I don't think we're just going to be, let me be careful here and not just draw it in the first octant. So okay, so this would be the generating line, right? And then the plane, of course, or at least part of the plane would go off like that. It'd kind of be slanting like that, right? So can you imagine what's going to happen then if you cut this thing? So it might be easiest to do kind of a side view, so looking at it from that perspective, so that I guess the x-axis the positive x-axis would be going off like this. So just drawing that line then, can you see what's going to happen? It's going to go off like that. So how would that corresponding plane then cut that cylinder? Can you imagine what that intersection curve would look like? So I'm going to erase that line because it's not really the part I want to draw. So wouldn't it be an ellipse? Something like that. And then, so this would be your curve of intersection. And then this would be the plane inside the cylinder. Does that seem reasonable to you? So that's what we're talking about as our C1. And then we're going to parameterize it. Looking down on it, that would be the counterclockwise parameterization, so that your normal vector points like that. Does that make sense? Okay, so that gives us an idea of what curve we're talking about. Now, what's the good news here? There is none. No good news at all. Well, the good news is Stoke's theorem. I don't mean to be a spoiler, but we don't have to evaluate this thing directly. We can use the right-hand side of Stoke's theorem. But what S are we talking about? I mean, there's actually an infinite number of S's that would work, but what's the one that makes sense to use here? It's a surface. It's got to be a surface, so you can't be talking about the disk. Is it really a disk? It's the inside of the oval shape intersection curve, C, right? Yeah, disk would have to be a filled-in circle. Yeah. So, so this guy is our S. Yeah, yeah. Does that make sense? Okay. So let's, again, do what this formula tells us to do. What does it tell us to find? Curl of F. So I'm going to erase this work of art right here. I know. And give us plenty of room to work. So let's first find the curl. Which I don't think it's going to be too awful. IJK, okay, d dx, d dy, d dz. Components, what are the components? Y, negative x squared, z squared. Okay, let's see if we can find this. So cross out the first column. What are you going to be left with? d dy of z squared is 0 minus d dz of negative x squared is 0. 0I minus, from the definition, right? Cross out middle column, we get d dx of z squared, 0, minus d dz of y. Oh, look, 0j, minus 0j. Is that okay? Yeah. Yep. And then cross out the third column, d dx of negative x squared, minus 2x, and then d dz, so what do we do? Oh, sorry, I'm looking at the wrong thing. We crossed that one out. So d dx of negative x squared is, there's the negative 2x. d dy of y is 1, so, and that's the part we're subtracting, so minus 1. Everybody believe that? Okay. So just curl of f, if you prefer component form, feel free. 0, 0, negative 2x minus 1. And then, well, we have to decide what we're going to dot that with. So in pictures, that guy's our surface, right? This part highlighted in red here is the plane, right? So, well, okay, so if you think of x plus z minus 1, subtract 1 from both sides, equals 0. If you think of this as g of x, y, z, then what is del g? 1, 0, 1. So let's take the dot product. What do we get? The curl of f dotted with del g. What does that equal? So just negative 2x minus 1. Okay. Everybody comfortable with that? All right, so let's set up the integral then. We'll say this, starting right here, that the line integral is equal to what? What's r going to be? Does everybody see? Good. Does everybody see if you project this plane segment down that's bounded by the cylinder, if you project it straight down, well, you're going to get the unit disk, aren't you? Yeah. So that r is x squared plus y squared is less than or equal to 1. And then, okay, so what do we get in the integrand? Well, yeah, I hope so. So if I factor out a negative, what do I get? 2x plus 1. Whoops. And then dA. Yeah. Okay? Everybody comfortable with that? All right. So then we're going to integrate over the disk. So if you project this guy down, and when I say this guy, I mean the guy in red here. We get the unit disk in here. So can you set up the limits of integration for me?
0 to 1, and
So the opposite of the integral from, if you set up the inner one first, so think of a radial spoke. It's RD theta, so 0 to 1 on the inside, right? Then 0 to 2 pi. And then I factored out the negative, so, 2x plus 1. What would that be? Yeah, okay, I'm going to do it like this. I'm going to take r cosine theta here, and I'll multiply out the r in a minute. And then, so I'm replacing x with r cosine theta, plus 1, and then r theta. And then what you said, Cameron, if you multiply out the r, you saved yourself a step. And we get, what, 2r squared cosine theta plus r.
And we can separate those from r.
I don't think so. dr d theta. Okay. Yeah, well, it's because of the plus between them.
Could you
right?
make it cosine theta plus 1 again?
Yeah, no, you'd have to totally be able to separate the function of theta from the function of r. You can't do it. So do you want to see me do this, or do you want to go on to another homework problem? Another one. Okay, so we'll say this is your setup, and I'll let you guys take it from there. It's not actually too bad.